In this entire series, we've covered a lot of things about making your first game. And today we're going to start on the last section, putting all of that stuff together into making a basic boss fight, including some basic programming, modeling, animation, some effects work, some sound effects, all of that coming together to make a fun and enjoyable introduction boss fight. So to do that, let's first start by making a new level that this boss fight is going to take place in. So we'll go into File, New level. I'm just going to make a basic new level, so we have a skybox and everything like that already implemented. And in there, I need to start deciding, okay, what are we going to do for this boss fight? And I'm going to keep it pretty simple. I'm going to make a octopus boss fight, where you have the main body, 8 tentacles, and the tentacles will slam down on a little platform. You have to avoid the tentacles, and jump on them to kill the tentacles. After 8 hits, no tentacles left, boss fight defeated. It'll be fairly simple, but it'll be good to keep it simple so that we can get something done and we can focus on polishing things up a little bit. So let's get started here by removing this whole platform that we have here and adding in our own platform with place actor, geometry, we're going to place that in a box. Location, going to reset that to 0, 0, 0. And then in brush editing mode, I'm just going to make this thing a little bit bigger. Alternatively, you could just come down here actually and make it bigger this way, so you have good control over exactly how big it's going to be. Let's make it 1200 deep and then 2000 wide. One thing that you'll want to do though is come to your player start and just move that up a little bit. Press the End key on your keyboard to snap it back down to the ground. And just walk around this. Let's see, is this too big? Is this too small for a boss platform? This seems pretty good. You don't want to have too much room to start avoiding these tentacles, but you also don't want to feel like there's literally nothing for you to do there. I think this is a pretty decent size to work with. Then we get to the boss fight itself, and here it is important to not go all out and make a super high fidelity octopus model and these very detailed tentacles right away, because what we're going to focus on first is essentially a block out. The same way that we started levels with blocking them out before we started adding art pieces to them. For normal enemies, it's also not a bad idea to do this. For bosses, it becomes exponentially more important because they are more complex and you want to test, is something fun? Then, once it is fun, you decide, okay, these are the actual assets that I need. You implement those, and then you start making them look and feel good. If something is fun without the visual component, it can only become more fun when the visuals improve. So let's focus on that first and head into Blender, not to make a super sophisticated asset at all, just to make something that works good enough. And here we're going to start off making just a rough body for our octopus. So what I'm going to do is I'm going to add in a mesh, and let's just do a UV sphere for that. Use numpad 1 to go into front view mode, and here I will alt select the middle loop here. Make sure that you're in edge select mode to be able to select these loops. Proportional editing turned on, and I'm just going to scale this down a little. Then take one of these upper loops and scale it up a little, pull it up a little as well. Take one of these lower loops, scale it up a bit as well, pull this down. For some reason, this middle vertex got pulled down. Didn't want that to happen. And probably make the upper part here a little bit more like bulbous. You can choose different fall-offs for proportional editing. Sphere probably makes more sense here now that I think about it. And you might need to pull up this middle vertex, going into vertex mode with 1 on the keyboard, just pulling this up a little bit more. Might want to add in a modifier here for subdivision surface as well. And then maybe the root version of proportional editing will work for this. Pull this down a little. And this isn't great, but it will do for now. I'm going to just pull these out here to have something that will approximate a mouth. Press I to inset, E to extrude inward. I'm going to add a couple of loop cuts here, just to be able to make 2 very simple eyes. And this is going to be our placeholder for our boss. It's going to be not great, but it will have to do for now. And I will make a armature for it as well. I will rename that Octopus. Go into the object data properties for it. Viewport display, set it to in front, so that's always going to be in front. Numpad 1 again, so that we're looking at it from the front view. At which point I realize that I need to R to rotate, Z to lock it to the Z scale, and then 90 to rotate it around. G and Z to move it up and down, and make sure that it is aligned to the 0 bottom line, which is essentially the floor of the world. Then In here, just extrude this out a little bit. We probably only need one bone for this entire bottom area. Well, let's actually make that 2 bones for this bottom area. Then one more extrude and Z to snap it to the Z axis. 2 bones for the upper body as well. Then coming down into this view over here, which you can just kind of orbit around into. Extrude out into the Y, Alt and P to disconnect the bone so that it's not cleared from the parent, but it is no longer physically connected. When we move it around, we want to look to the Y-axis as well, and we're going to just make this thing line up with the little snout that we made. And you might need to move this a little bit into the X because I rotated this weirdly. This is just a temporary prototyping model. It doesn't matter if it is a little janky. And as such, we can just select the model, Shift and select the armature, Control and P, armature deform with automatic weights, and now we have a skeletal mesh that we can, in theory, at least kind of animate a little bit. Again, it is really bad and really janky, but it'll do for now. Probably do want to shade this as auto smooth, and we can, well, save this and export it. So save it into some location, then we're going to just export this, export it as an FBX file into that same location and drag and drop it in to Unreal. We can just import it. Everything, basic settings should be good enough. We import this as a skeletal mesh. And this is going to be our boss. It's a very intimidating little fella, isn't he? And we'll do the same thing for a tentacle. And I guess we can do that in the same file. And I'm going to add a single vert. If you don't have that option in Mesh, you might need to come up into Edit, Preferences, and then in Add-ons. If you look for Mesh, you will have extra mesh objects. Single vert might be a part of this add-on. It's an add-on that comes with Blender by default, so you should be able to find it. I'm not entirely sure if single vert is part of that or not. I think it might be, but we're going to be adding it. So a single vert, which is just essentially nothing. So let me just, for the time being, disable the octopus, and the single vert, if we focus on it with numpad period, is just, well, nothing, more or less. So before we do anything else, we want to be able to see what we're doing, right? In modifiers, what we can do is we can add in a skin modifier, and that will just add geometry to our single vertex. If we then add a subdivision surface modifier as well, it just kind of rounds it out a little bit more. And then once we're in edit mode, make sure that you're in single vertex mode, and then you can just start extruding upward. So just E to extrude, and then Z to lock it up in the up and down direction. And the wonderful thing here is if you press Ctrl and A, you can scale up the single vertex, and that way you can make this into a tentacle that tapers off toward the end here. So we're going to just add in a couple of different points. The last one here being relatively thin. If you go into wireframe mode, it's a little easier to see the individual vertices. And we're going to just kind of scale up all of these different vertex points to make, well, a tentacle. There we go. We can move it to the side a little bit to check how it compares to the size of our octopus. And it's a little big at the moment, I would say. So maybe just scale it down a little bit. And now it's a little bit thick because the thickness of this entire thing comes down to the individual vertices. So you do need to go back into edit mode, select everything, Control and A, and then just thin it out a little this way. But that's going to probably be a pretty decent spot for this to be at. And we can maybe even make it a little bit taller and make the octopus invisible again, and just give this an armature as well. So we'll add in a armature, single bone. Again, go back, make sure that this is in front in your viewport. Numpad 1 to look at it from front view mode. Probably want to move this a little bit more to the right here. And then going back into the armature, which will give the name tentacle, by the way. Just press F2 on it and you can rename it. In edit mode, just add in a couple extra extrusions. They can all pretty much just go upward. There's nothing like too majorly interesting about it. Do make sure that you have enough bones here. It is really easy to just say, 3 or 4 bones is enough, and it probably will be for the prototyping stage of it, but tentacles require a lot more bones than you might initially think. Like 10 bones for a tentacle definitely isn't even overkill. It's pretty reasonable. And then here, I'm going to just apply the skin and subdivision surface modifier. So now this is actual geometry. And that is important for the pairing it with automatic weights so that I can actually use all of that information to apply the vertex weights. And now we have the tentacle as well. It's very bare bones, it's very basic, but at least we'll have some assets that you can make in literally 10 minutes. I made this in 10 minutes while explaining all the steps to you. So you don't need to use straight up just literally only gray boxes. You can make super quick, easy little placeholder assets like these. And especially since a lot of the things that we're going to do are going to be based on having some sort of animation, making rough placeholder animations with these also really, really quite nice. So we're going to select both of these as well now. Just box select both the tentacle and the armature. And then we export as FBX. This time I want to make sure that only either the visible objects, or I like doing the selected objects, so that it doesn't export everything in the entire project file. And I'll call this like tentacle FBX, something like that. And then we can just drag and drop that into. If it tries to merge with the existing skeleton that is in here, that might be because it is in the exact same Blender file and it kind of gets confused. So you might want to just make a tentacle folder for it here, and that should prevent all of that from being an issue. You can just import it and everything will be fine. And now we also have the skeletal meshes for the tentacles. That's a lot of preamble for us to just have some temporary assets, but it's going to make things a little bit more reasonable than just having a bunch of literal like boxes to work with. So now, how is this going to work? You can put this together in whatever way you want, really. The way that I'm going to do it is we're going to make two separate actors. We're going to make an actor for the body, and that's going to hold all of the AI logic. And then we're going to have separate actors for all of the tentacles. That way it's easy to delete the tentacles as we defeat them one by one. And it's going to be easier to move them around in the world to specific spots, tell the specific tentacles to play specific animations, instead of all making it into one giant blueprint with all components instead. So let's make this blueprint class for the actor. We'll call that BP Octopus Boss. And in this blueprint, we're going to add in, well, a skeletal mesh, of course. And the skeletal mesh asset that we're going to be using will be the octopus body, which can have an animation blueprint, and we might do that in a moment here, but for now, that's all it's going to do. And then we'll add in a state tree component as well. That is going to handle all of the AI stuff for it. We can place this into the world. I'm just going to place this right off the edge of our boss platform here, somewhere around there maybe. And then let's make the tentacles next. So we'll make another blueprint, actor, BP, tentacle. And in there, again, we add in a skeletal mesh component, but this one doesn't need to have any AI. This doesn't need to make decisions. This is just going to hold functionality that the boss itself can call when the boss decides it needs to do something. We'll just add in the skeletal tentacle mesh for this. And then the boss could just spawn those in, or alternatively, what we could do is we could just place these in manually around the boss, which is what I'm going to do now. So we'll just do like 8 tentacles here. That's 3. It's very unsymmetrical and very, very ugly, probably. Oh yeah, it is. A tentacle should be able to do 2 things. Number 1, do its slam down animation as an attack. And number 2, be given a position along our playing field here where it should do that. Let's focus on the animation first, because that is the easier part. So what we're going to do is I'm going to make a level sequence here. I'll call that tentacle attack, LS for level sequence tentacle attack, actually. And we'll just pull in the asset right from our content browser. And what that'll do is it'll make a level sequence where it spawns in the asset that we're working with here. That way it doesn't need to exist in any level. And matter of fact, we can now open up the sequencer no matter what level is open, and it will work to let us adjust this. It's always just going to spawn in at 0, 0, 0. Let's add in a control rig. And we don't have a control rig made for this. And ideally, you probably would want to make a control rig for this, obviously. And we will in the future. But for now, again, we're prototyping this. We don't want to spend too much time making a control rig for something that we're going to throw out anyway. So what we'll do is we'll just add in an FK control rig. And all that is just a whole bunch of literal bone controls. So we can just say, okay, we want to rotate this downward, and that's kind of everything there is to it. So the attacking animation. It's going to start being entirely underground. So we start at the bottommost bone, and we make sure that that is very, very load down here. Just make a starting keyframe for everything. Have it take about 10 frames to come up to roughly the surface. And in that time, maybe all of these segments just bend back a little bit. With the tentacle, it oftentimes is very nice to have a little bit of a delay between every single segment of it. So what we can do is we can offset these by a couple of frames each. And this doesn't take that much more time, but it does make it just a little bit more lifelike, and it just feels a little bit better. Then I'm going to have it wait for a couple of frames, let's say up to frame 30, set one more keyframe, and then it's going to take, let's say, 8 frames, and everything is just going to slam down super hard. And this, once again, we can technically offset a little bit so that it feels like it really is whipping down on the player. Then we just have it hang out for, I don't know, let's say frame 55 is where it ends. We're at 30 frames per second. Let's give it 3 seconds, so another 90 frames. That would take us up to frame 145. That's another keyframe. At which point, let's just copy over all the keyframes that we had here before at the bend back pose that we had. Give it something like 10 frames to get back into that pose. And then we make it just go back under right away after that. Another 10 frames or so. And now we have a simple animation where it goes up, slams down, gives us a little bit of time to jump onto it, and it goes back up and down, and it resets to where it should be. And that's the animation. So let's just right-click this and create a linked animation sequence. We'll give that the name AS for animation sequence. Tentacle attack. Okay, we export that. That's pretty much all there is to it. Now we have the animation that we can use for our prototyping, but in order for this to actually do anything, we do need to add in a bit more in terms of either components and or code to our tentacle blueprints, which again is really why we're making these separate actors, because it's very easy to just add in a box collision as a child of the skeletal mesh and just say, okay, I'm going to attach you to, let's say, a bone segment number 3. And then it becomes super humongous, which is totally normal, totally natural. We just scale it down a little bit, and then we can set this to be whatever size we want it to be. And I'm going to just use this as a single, simple hurt box. Ideally, what you might want to do is you might want to add in a collision box for every single segment here. That way it's a little bit more accurate, but it also becomes a bit more tedious to take care of. So this will be the hurt box. And then I'm going to copy this over by just selecting it and pressing Ctrl and D to duplicate it. And this will be the hit box. The difference being, this is the thing that's going to be hurting the player. This is going to be the thing that is going to be driving the player hurting the tentacle. And as such, usually we make the hitbox a little bit bigger than the hurt box. And if you don't see it showing up, it's because it's not at the same parent socket. So just set it to bone 3 as well. And then we can see, just make this a little bit bigger. And by default, both of these things are going to be not generating overlap events. So we go down here into the collision settings and generate overlap events to false for both of them. Because with that, what we can do is in the event graph, make a custom event for that hurt box. And then we get our hurt box and we set generate overlap events to whatever we give in here. So in this case, it's going to be hurt box true or false. And then we do the same thing, custom event for set hitbox. We just get a reference to our hitbox. We set generate overlap events, pull this into the event as an input parameter. And now we can easily call this from, in our case, the animation, but we could also explicitly call this from the boss if for some reason we want to, based on some AI thing, enable or disable either the hurt box or the hitbox, whatever. We're going to stick with it just being based off of animation for now though. And with that, let's go into the tentacles animation. And what I'm going to do is I'm going to make an animation notify state for both the hitbox and the hurt box being turned on or off. And the way that we do that is just in blueprints. We can make a anim notify state by coming down in all classes and looking for it. And let's call that ANS for animate notify state, hurt box tentacle. At this point, I am very specifically scripting out a notify state for a very specific enemy. Usually you wouldn't do this. Usually you would have a more structured way of dealing with this, like setting up a blueprint interface so that you can use this notify on anything that has a hurt box or a hitbox to enable or disable it. We don't have that all set up now, and while I'm telling you about it now as just a good bit of knowledge to be aware of, it might go a little bit beyond just getting started with the engine and making your first game. I have some other videos on how, why, and when you can use Blueprint interfaces, and they're really, really cool. Just want to mention it here. For now, don't worry too much about it, but this is a very hard-coded, specifically scripted way of doing it, and usually you try to avoid doing those things as much as possible. But in an animation notify state, we have a begin, an end, and a tick. We'll program those in a moment, but just so that you understand what those mean, is in our notify tracks here in the animation, we can add in notify state in our case, and it now adds in the notify state that we just made with Blueprint, ANS hurt box tentacle. And this allows us to, if we zoom in a little bit, make a state inside of our animation that is going to, the first frame that we enter the animation, run, well, begin. Any frame that we are inside of the animation is going to run the tick event inside here, which we're going to not use at the moment, but you can. And then the first frame that it exits the animation is going to run receive notify end. Both of these are things that we want to work with at the moment. Do be aware that these notify state blueprints are a little off because you can't set variables in them. They are read only. So all that it can do is just run other functions or take in information and run some functions based on them. They can't really be used to change data. But we don't really need it to change any variables or any data, because on begin notify, what we do is we get the mesh component that this is being run on, and we get the owner of it. Because this code is currently running on the mesh component, so it's going to be running on the skeletal mesh here, and the owner of that skeletal mesh is going to be our tentacle actor itself. So we get the owner, and we can see that the owner, if we hover over it, is going to get us a actor object reference. That's going to be a generic actor, so we need to tell it, hey, we actually are looking for a cast to our BP tentacle. And if we run this animation notify now on anything that is not a tentacle, this cast is obviously going to fail. This is where you would replace it with a interface usually, so that you can use this in a whole bunch of different scenarios. For now, again, we're going to stick with this. And then we just set the hurt box that we just made. And when we begin notify, so that's this function, we set generate overlap events to true, and then return value of this function doesn't matter that much, but usually you tell it to return true. That just tells it that it successfully did the thing it's supposed to do. And then in the notify end, we're going to do the exact same thing. We're taking the mesh component, getting the owner, casting that owner to the BP tentacle to try to get a reference that's upgraded to the type that we need it to be, and then we just set the hurt box to being false. And now we've got a very easy adjustable way of, inside of our animation, setting our hurt box to being either true or false. So when he starts moving down with the tentacle, we want to set the hurt box to being true. And then when he lands, just give it a couple frames extra, and then the hurt box is no longer going to be true, because starting at this point, we want to be able to jump on it. And for that, we just duplicate our animation notify here, and we'll call this hitbox tentacle. And opening that up, because we duplicated it, the code from the previous one is still in there. All that we do here now is we just set the hitbox instead to being true on begin and being false on end. It really can be as simple as that. So just copy this over, hook everything up in the way that makes sense. And just like that, we have the hitbox for the tentacle as well. So we can add in a notify state for that as well. Now that we've made it, it shows up in this menu. So the hitbox for the tentacle, we turn it on pretty much right away after the hurtbox turns off, and then we wait for it as long as it remains stuck on the ground like this, and it looks a little bit suggestive from this angle. It's going to have the hitbox turned on, but then as it goes up again, the hitbox will be turned off, and we just have it go down. This is why we made this temporary asset, because now we can do these kind of things entirely driven off of the animations, instead of having to have a bunch of delays in our blueprint logic, which are going to be bothersome and annoying to adjust. Just really quickly making this as an asset so that we can properly use animation notifiers and that kind of stuff makes even just prototyping things a lot easier. So then all we need to do is make a custom event, which is play attack. That's going to get our skeletal mesh, and it's going to play a animation, and the animation that is going to be playing will be our tentacle attack. This is the simplest, most straightforward way of doing this. And then we just need to script out what happens when we overlap with the hitbox or with the hurt box. So with the hurt box, we just select it and scroll all the way down to on component begin overlap. And we got to check real quick because I don't rightly remember every single thing about this project. In the player, I assume that I have implemented some sort of damaging code already on the player, right? I have. Event damage. So we can just use Unreal's built-in damage system to say, hey, other actor, just apply damage. And I assume that I went with an easy, just we have 100 HP to start with, right? Nope, we have 5 HP to start with. That's fine as well. So that's going to do 1 damage. We have the damage causer, which is just going to be a reference to itself. And then the event instigator probably doesn't matter in this case, but it's going to be the controller of the octopus boss itself. And I'm assuming that we're going to set the octopus to be the owner of these tentacles. So we could get this from get owner and then get AI controller and give that into the instigator, just in case it ends up mattering. It probably won't. And then the hitbox we probably will take care of a little bit differently. I'm going to compare this with how we've dealt with the enemies in the past. Because here we check if it is a player pawn, and we caster the character, and then we destroy the actor, and we run a function based on that. So we're going to pretty much just do the same thing here. We have the hitbox. On component begin overlap, we check other actor. Is that equal to get player pawn? Because if we're overlapping with the ground or anything, we don't want anything to happen at all here. And I'll do you one better. We also want to check if the player pawn is currently moving downward. We don't want to kill it if we just walk into it. We only want to kill it if we jump down onto it, which is also what we're checking for here. Again, this is pretty much what we've done in the past as well. So we cast this to just the character class so that we can get the character movement component from it. And make sure that this is hooked up to your branch node as well. So if this is true, then we do the cast. And then we get the velocity from our character and we check, hey, if we break this vector open and our Z is less than 0, that means that we're moving downward. That means that we just jumped onto it. So in that case, I'm just going to copy over some of the code that we wrote before for the base enemy, because we have a launch character here. That is our current Z jump velocity multiplied by 1.5, and we do a client camera shake. So we pretty much just copy that over. That's fine, and paste that back in here. And at this point, it might be a good idea to set this launch character and this camera shake to be handled by the player itself, so that we have that set up in one location, because we're pretty much doing the same code in 2 different locations now, and that is usually not a great idea. So let's, instead of putting that into the tentacle itself, let's just refactor things a little bit on the fly. Go back into our player blueprint. We can just make an event out of that, right? We can just say make a custom event in here, and we'll call that bounce attack, or attack bounce, or bounce from enemy, or whatever we want to call it. And there, we just paste in all this stuff, and we just launch character up with Z velocity times 1.5. And instead of getting the character movement from a reference, we can just drag in the character movement from our player here, put that in there. And it will also always start that camera shake now, and that's now all just contained on the player itself. So we can call that from anywhere that we want. So in the base enemy, instead of doing this, what we want to do is this player is going to get cast to our BP player character, and we run that bounce attack instead. Just to build some good coding habits in not duplicating the same code all over the place. That also means that this cast that we have here probably can just directly be a cast to BP player character, because we're going to need a cast to that anyway, since we're going to be using a function that exists on it. So just replace that, and then we still have the character movement check to see if we are moving downward. But if we are moving downward, then we can just do our bounce attack or post bounce attack or something like that. It probably should be called. And we're running the same code from 2 different locations now. And then we also just destroy the tentacle itself. And with that, we now have a working tentacle for our boss fight. So let's put that in here. And just as a little bit of a test, what I'm going to do is I'm going to put one tentacle back here. To open up my level blueprint. With that tentacle still selected, I can right click and create a reference to it. And on begin play, what I'm going to do is I'm just going to set a timer by event. And this will let me connect up a event to the event input pin here. And say, well, every 6 seconds, maybe. Set this to looping. I want to run whatever code is in here. And whatever code is in there will be our play attack. So now every 6 seconds, it's going to play that attack animation. How long is the attack animation to begin with? It's a good question. It's about 6 seconds long, so it's going to pretty much be looping indefinitely here. Let's also save this level while we're at it. So we'll just call this boss level. And let's see if, first and foremost, our thing is even playing the animation properly or not. And we need to wait 6 seconds for the first iteration of it. And it does. It goes up a little bit too high, so that's probably something that we want to take into account here. But if it hits me, it should... There we go, damage me. And if I jump on it, it dies and I have the camera bounce. And let's go back real quick into the tentacle because the animation itself just has it go up too high. And that probably is just entirely due to the fact that I'm animating its location up a little too much. So we go from location Y being 8 to it being -1. This should just be 0. And we can delete that keyframe, replace this one with 0 as well, and have it go back to being 8. And now, if we update this sequence or animation, because everything is done in Engine, we're animating everything here in Engine, it's going to immediately update the animation sequence as well, and you will see in a couple of seconds here, everything will just immediately be reflected with the new one here in-game. However, these tentacles don't even nearly reach back far enough for this to be a good boss fight. So we'll probably either want to make this platform a little smaller or make the tentacles a lot bigger. And I think the answer to that is maybe a little bit of both. So I'm going to go in here and open up my tentacle blueprint. And first and foremost, our skeletal mesh, I think I'm just going to set this to being 1.6 times the original size. So that should pretty much give me more or less, I think, enough room for it to hit almost the entire platform. There we go. And then the platform itself, I'm going to make a little smaller as well, just by, I don't know, like 2 steps here. And I'm maybe making it a little smaller in both of these directions as well, so that we really don't have that much room to avoid these. Yeah, this is a pretty small platform. This might be a little too small now, but this is again why we prototype this stuff. So there we go. We've got the tentacle set up. We've got our basic platform set up. I think next time what we're going to do is we're going to make, instead of this tentacle just being a single test that we have, we're going to make this octopus itself, which probably also now needs to be a little bit bigger because its tentacles are kind of huge for its size. So let's make this just like twice as big. That seems a bit more reasonable. We're going to make this thing decide which of its tentacles and when it's going to be using it to attack and where it's going to be attacking from. We have all of the basics for it set up now, so the proper AI programming is up next. Previously, we got to start with making our first boss fight here. This really ugly little prototyping octopus. And we've made these tentacles be able to attack. We can kill the tentacles and... well, that's the basic 2 mechanics of the boss fight, but we don't have any AI to actually drive this or any behavior, well, at all. So that's what we're going to be focusing on today, setting up the basic behavior of this boss fight to start properly prototyping this thing. And it's not going to be that difficult. Last time we spent a lot of time setting everything up, but that is going to pay dividends right now. First things first, this actor, the central bit that we have here, if we just have it highlighted and press Ctrl and B on the keyboard, we're going to browse to it in our content browser. It's going to need to be able to keep track of the tentacles that we're using here. And we can do that in a variety of different ways. We can either just make some tentacle references or a tentacle reference array and manually fill these out. But since we know as programmers, as level designers, that this character is going to exist in its own little bubble, its own little level, with just a couple of tentacles surrounding it. There's not going to be any weird fringe cases where this exists in some other level where there might be tentacles existing somewhere entirely else, separated from it. We know that we can take a little bit of a shortcut, and we can do that with get all actors of class. Now, it does say that finding all the actors will be slow. It's not that slow. Is it something that you want to be doing on Event Tick on a bunch of different actors? No, you don't want to be doing this too often, but the warning here saying that, hey, be careful, this is extremely slow, isn't actually accurate. It's outdated, just never got updated. We can give in an actor class, so a specific blueprint that we want to find, and we want to find all of the tentacles in the world. And it's just going to output an array of all of those tentacles. And if we promote that to a variable and just call it tentacles, there we go. We have every single tentacle that exists in the level that is loaded currently. Again, we can easily do this because we know that we're putting together this level in such a way that the only tentacles that will exist alongside with this boss body will always belong to it. If you know that you might have a boss body existing in a level where there's tentacles of that class or any subclasses from it that shouldn't belong to it, this is not going to be a thing that we can do, and we do need to explicitly expose this as a instance editable variable and manually go in here and just select these tentacles like this. And that's totally doable, but it gets a little tedious to do. If we know that we can get away with this is fine to just do on begin play. Tentacles will be handling their own destruction, and anytime that we destroy a tentacle, we want to send back a signal to this to, number one, remove it from this array so that we can easily keep track of how many tentacles still exist, and so that we don't accidentally sample a tentacle that doesn't exist anymore from this array. But we can also use that signal right away to maybe drive some AI improvements. Maybe we have a couple of different phases with different attack speeds, and once we're below 5 tentacles, it goes faster, and then the last 3 tentacles go even faster, something like that. And the way we can do that is with a for each loop. This is going to loop over everything in this array and do whatever code we put in here for each element in the array. So we can just assign onDestroyed, and that will just run whatever code we put in here when any of these actors get destroyed, and it will give us a reference to the actor that was just recently destroyed. And the wonderful thing about that is because we have that, we can just get our tentacle array here, and we can remove an item, the thing that was just destroyed. This does give you a generic actor reference though, which can be a little annoying. So you can either set this tentacle array to be just a generic actor array, or we can just cast this to the tentacle class, which honestly is fine. There's another one of those things where I have a bunch of videos on the channel talking about casting, when it is good, when it is bad, what to think about. That's somewhat more intermediate stuff. If you're just getting started, you're going to have a lot of people telling you that casting is the devil, and there is good reason for that. For now, don't worry about it too much, but do know that it is both bad implications for both performance in some cases and building bad coding habits for long term if you want to grow your skills as a programmer. In this case, it actually is fine to do, not just because you're just trying to get used to it and you're just trying to learn. This would just be a legitimate use of letting you use casting. Again, if you're curious about that, finish this series and look up a couple of videos on my channel about when it is okay to cast, because it can totally be. Anyway, we remove this from that array so that we get a progressively shrinking array as these things get destroyed. Which means it is time to start making the state tree for this guy. So let's go into our artificial intelligence tab, make a state tree. I'm going to just make it for a normal state tree component, even though we're making an AI. The difference being, I've talked about this a little bit before, state tree components have normal versions and AI versions. The normal versions you place on an actor, and then the actor itself can do all the logic and all the decision making and just run the AI. State trees still are AI frameworks, even if it's not a state tree AI component. The state tree AI component just specifically is made and optimized to be run on an AI controller instead. The upside to that is that you can make generic behavior that the AI controller can run and can apply to, well, anything that it possesses. I personally hardly ever use the AI version. Call that ST for state tree, octopos, and we'll open it up. And we're going to just make a very easy loop here to start with. Let's add a state, and that state will be attack. It's just going to do an attack. Then we're going to add a state where we will have it wait. And that's going to be the entire loop. So we'll make an attack task here in a moment. We're going to set up the transitions first. So let's set a transition. Once the state is completed, we go to the waiting task. And then the waiting task, we can just immediately add in a delay of a duration, let's say 1 second, with a deviation of a quarter second in either direction. Once this state, so this delay is done, again, we just add a transition on complete and we go back to attack. Congratulations, we've now made a logic loop. But we need to make the attacking task. So let's do that. We can go up here in new task, just make one of the blueprint base. And since this one is going to be specific to this boss fight, instead of putting it in my AI folder, I'm just going to put it in the boss fight folder here. And I'm going to call this state tree task octo attack. We add in the state enter. And at this point, we can add differing levels of complexity to what we want to do. No matter what we do, though, we want the context actor class for this state tree to always be our octopus. So octo, what did I call it? Octopus with a V, because that makes sense. And when we set that up for this state tree to be the context actor class, we can easily now in this state tree task, make a variable. I call it whatever we want. We can call this just boss. And as long as it is also of the same type, so the octopus boss type, we can give it a category of context, which is important that you don't mistype it. And this is automatically going to just pull through the owner, the context of this state tree, and put it in this variable. So we don't need to manually set the value. We don't need to do any weird getting. It's just going to handle all that for us very smoothly, very easily. And in there, what we do is we get the tentacles array. From there, we just get a random array item. Now, this is where we can do things a little differently, because ideally, and we might do this in a moment, you would set this up so that it picks a tentacle in either just a sequential order, or it picks a tentacle that is not currently already performing an attack, because in later stages of the fight, you might want to have 2 tentacles attacking at any given time, at which point you want to make sure that you're not picking one that is already mid-attack and all that type of stuff. We'll worry about that in a bit. For now, we're just going to pick a random one, and we'll just make it play an attack. And here, again, you can choose things a little differently. You can remain in this state until that attack is done, and then move on to the next state where you wait. Or you can just immediately end this state and just spend a lot of time in that waiting state instead. In this case, it doesn't really matter. But if you have something where the state tree task itself here takes care of, for instance, damage application, you want to stay in this state until that is taken care of, and then you can move on. For now, though, we have the tentacle actors themselves taking care of applying damage, so we don't need to do that. So we can just finish our task and say that we succeeded right away. This is the easiest version of just making a random tentacle attack for now. We're going to need to come back to this in a moment. But to make sure everything is running smoothly, let's just get started with that. Going back into our octopus boss, we'll set this state tree to be, well, our octopus boss. And now, if we go into the level and we make sure that it starts the logic automatically, we do need to add that task into our attacking state. So let's just say state tree attack octopus task. And after we've done that, now it will be doing the animation on random tentacles. But as you can see, it doesn't wait for one tentacle to finish before the next one attacks. And it doesn't even like move them in close to me. So the ones in the back literally do nothing at all, which it's not a very difficult boss fight so far, is it? We needed to also pop up at a random place between the 2 edges of our platform. So how are we going to do that? Well, for that, I like to use these things called target points. So we have one target point here, and then we're going to just copy over the target point to the other side. And target points can be used for a bunch of different things. I often use them for laying out patrol routes for AI enemies that need to patrol. But in general, all that they are just an actor that doesn't really have any code and just serves as, hey, you represent a location that something else is going to use in some way. And that's exactly what we're going to do here. So our boss, if we open up the blueprint for it again, what it's going to do is it's going to have 2 variables. It is going to have target point start, and that's just going to be a target point actor object reference. We'll make that instance editable, and then we'll duplicate that over and call it target point end. And with both of these target points now, if we go back into the level, we can say, hey, this is the starting target point, and this is the ending target point. And we might actually want to move these up a little bit so that they aren't exactly on the edge here of our platform, but they exist a little bit pushed back, because we're going to be moving these tentacles to a random point between these two targets. In the octopus attack task, before we play the attack, what we'll do is we'll get that random tentacle and we'll set the actor location. And now we just need to figure out the way that we're going to be getting that location. But we already have a reference to our boss here. So we can just get target point end and get target point start. And if we just get the actor location for both of those, it's going to be super easy for us to get a point randomly assigned between the two of these. Because we can just do a lerp, which is linearly interpolating between 2 points. So we give in point A and point B, and then the alpha, if it is 0, is going to give us this point. If it is 1, it's going to give us this point. And if it's anywhere in between, it's going to just proportionally give us whatever is in between these. So 0.5 would be a point exactly in the middle of these two. 0.1 would be a point very close to this one. 0.9 would be a point 90% away through to this one. And we can just get a random alpha by getting a random float in range. And that range is just going to be 0 to 1. Congratulations, we've just made this thing randomly set its location on a line. That's still going to require us to do a little bit of extra work here, but as you can see, it is now actually putting the locations right here. And with 1 second intervals, this is a pretty hellish boss fight for me to deal with right now. There is the issue that they don't go back to their original location at the end, which is not ideal. So that's the next thing that we're going to be fixing. At the end of whatever attack we do, we need it to go down, and then we need an animation for it to pop back up, and we need it to play that animation after we reset it back to its original point. Let's first do the animation part of it. We can just duplicate over the animation that we already made, and let's call that level sequence tent reset. And if we open it up, before we do anything here, before we even save it, we want to right click this and create a new linked animation sequence, because this is now still linked to the animation that we made before. And if we save this, it's going to override it, which we don't want to do. So we create a new one, call it animation sequence tentacle reset as well. Just export that, that's all good. And then all we needed to do is we just needed to do the first part of the animation, really. Don't even necessarily need it to do all of this bending back. We just need it to pop back up like this. And that's really all there is to it. Just have it take a little bit more time. Takes a second for it to pop back up there, just so that it's a little bit less aggressive. Of course, this is not an attacking animation, so being a little bit slower is probably good. Pull back the end of the animation here so that we have it be the proper size. Save it, we have the new animation. As easy as that. We're going to, however, make both of these into animation montages now. So if we just right click these and we create animation montage, it's going to make a montage for both of these. And the reason that we do montages here instead of just playing animations like we have so far is purely from a scripting perspective at the moment. Going back into the BP tentacle, right now what we're doing when we say play attack is we just play an animation. And playing an animation, it just plays it. It doesn't give us any feedback of when that animation is finished playing. We can set it up to do that, but it's much easier to just say, hey, play a montage, because that has a bunch of output pins that just tell us, hey, when is the animation here completed. Playing a montage, however, will only work if we have an animation blueprint that supports playing a montage. So we'll also need to make a quick animation blueprint here in a moment. But that's going to be really easy. We don't need to set up any logic for it or anything. We just needed to have an animation slot. So we just play the attack montage, the one with the blue colored little bar here at the bottom, not the green one. And then once it is completed, what we'll do is we'll once again play a montage. And this one we're going to play the reset. In between that though, and also hook this up to complete it, not the top pin. In between those, we're going to reset this thing to its original position. And in order to be able to do that, it needs to remember its original position. So we go back to begin play here, and we're going to make a variable for that. and we'll call that start location. It's going to be a vector type, and we just drag that in, holding down Alt to get a setting node. And at begin play, all that we need to do is get the actor location and just set our variable to that value. Now the actor itself is going to remember where it started the game at, so we can set it back to that location. And we'll do that between these two montages. So after it's finished playing the first montage, it'll be underground, so we won't see it teleporting. We will set the actor location, and we're going to set it to wherever it started at which point it can then pop up back with the next animation montage. But as I said, for an animation montage to work, it needs to have an animation blueprint. So go to the skeletal mesh assets, and we can go up to create an animation blueprint. You can just keep with the default name and put that in as the animation class here. And as I promised, we're not going to have to do anything weird. We might end up making an idle animation here, obviously, once we get around to doing that. But for now, all we need to do is just add a animation slot, which is called a montage slot. Slot default slot. That's all that we need to do. Now it is entirely capable of playing any animation montage that is set to the default slot and the default group, which at the moment it doesn't have anything more than that. So that'll do just fine. So now what we want to do is we want to make sure that we can't pick a tentacle that's already attacking to do an attack as well. And that we can again do in a bunch of different ways. I'm going to keep it in the attacking task itself though. Instead of randomly sampling from the array of tentacles directly, we're going to make a separate array of choosable tentacles instead. And we'll need to keep track of whether or not it is in a choosable state. And I think the tentacle itself is going to just keep track of that in a bool. So let's make a variable in it and call it just is attacking, something simple like that. And it will be Boolean. And when we say, hey, you're going to be playing an attack, the first thing we do is we set this to true. We say, yes, I am now in fact attacking. Then it's going to play the attacking montage. It's going to set back to the original location at the end of that montage. Then it's going to play an animation that is going to make it reset back upward. And then once that one is completed, only then do we say, hey, I am now no longer is attacking true. So is attacking we set to false. With that, it is now super easy to just get is attacking. And if it is attacking, we just don't do anything. Only if it is not attacking, do we add it to a new array. And we'll make that array as a variable on this task. And we'll call that pickable tentacles. And we'll make that of the type BP tentacle object reference. And we'll change it into an array over in the details panel here. And then we'll just add a item. And we'll add the array element from our for each loop. We're pretty much just filtering on any tentacles that are now considered pickable. Then, once that for each loop is completed, we can do the set actor location stuff. And instead of taking a random array item from our boss's tentacles directly, we're going to take a random array item from the pickable tentacles. And let's see how that works. It's going to pick one, and it didn't quite move it to the front of the line there. So let's try and figure out why that is. Here we have something interesting. This is a thing that is important to note. There is an issue that we have here, and that is that we have this pick random tentacle going into set actor location, and then pick random tentacle again into playing an attack. Because these are pure nodes, they are nodes that don't have one of these execution pins, they actually kind of get called in reverse. The functionality of these nodes, which in this case is just picking a random array item from this, gets rerun every time a node with an execution pin requires their inputs. So what this is doing is it gets to this set actor location. It sees, hey, this target is getting from a random item in this array. It gets a random item. Then it moves on to play attack and it looks back. Oh, I have an input here. Let's see. Okay, that's random item from this array. And it runs this randomization again. We don't want that, obviously. We want to pick one random thing and just use that one for both of these actions. So what we're going to do is either set this to have execution pins. That way it will just do it once, and then anytime any new node asks for this, it's going to remain with that same value. Or alternatively, something that might make a bit more sense, logically, is just promote this to a variable instead. At which point you don't need to have the execution pins for this. So we just put this in as a promoted variable instead. give it a name, picked tentacle, and then instead of directly connecting these up to this random array element, we use that new variable that we just created for it. Either way works. This is a little bit more like explicitly obvious, the fact that you're setting it to a variable. So generally that is what I prefer it to do. And now you should see that it will do this properly. It spawns them in at, well, it moves them in to close to where the player is. And then it just slams things down, waits a little bit, and then as it gets to the end, it teleports them back. And it feels a little bit jumpy and janky because we can see it teleporting all over the place. So let's just add in a quick little plane here to serve as essentially the surface of the water. And it still has a little bit of a jumping issue, and that is because it is blending the animations, and we don't want it to blend. By default, animation montage, as you can see, has a blend time of a quarter second, and that can cause really weird things when you have things moving around in the way that we do, because we want it to just snap into the animation. It is entirely random where it slams down. So now that our basic attack for our boss works, I think next time it is important to start working on having these bosses at different phases. We have the basics of a boss fight that is trying to damage us and that we can instead damage sort of in return. There's still a lot of work to be done here. But for now, I think it is important to make this guy also have different phases. That is what generally improves a boss over just a mini-boss or even a normal enemy, is the fact that as you progress through the fight, it becomes more difficult. And really, that's not that difficult to implement from what we already have set up in the previous parts. So let's open up the state tree again, because the state tree itself, we're actually going to turn into a single phase. So let's call this the Octoboss phase instead. And we'll add a couple of parameters here, because instead of the attack just being a hard-coded 3 seconds with a random deviation of 1 second, we're going to promote these just to some parameters. Just promote a parameter in global parameters, and we will see it showing up in our parameters, the duration. We can rename this to delay between attacks. And then this one, what we'll do is we'll do some math on and set the random deviation to just be 0.1 multiplied by that same parameter. So it's going to just always have a random deviation of about 10% up or down. And that is everything there is to this. That just makes this into a reusable little state that we can use. So with that, let's make a new state tree component, and this will be the actual state tree for the Octopus boss. Let's open that up and just add in a new child state, and we'll call this phase 1. And instead of adding in code directly to the tasks for this, we're going to change this from type state to a linked asset, and the linked asset is going to be our boss phase. Now we can see the parameter values that that asset has, and I just noticed that I made 2 parameters for it. Did not mean to do that. Let's remove this one and make both of these work over the same parameter. That is might be parameters, delay between attacks. There we go. We have that as a parameter for this. So we can say the delay between attacks for the first phase is going to be like 7 seconds. And then we just Control D to make phase 2, going to be the exact same linked assets, but this is just going to work off of, I don't know, 4-second intervals. And then phase 3 at the very end there is going to work off of 2-second intervals. And now if we make a little bit of code for it to go from phase 1 to phase 2 to phase 3, we almost didn't do any programming, and we've made a boss progression that becomes more difficult as the fight goes on. Of course, in a proper full boss fight that isn't so simple and so introductory, you probably would have entirely new mechanics showing up and entirely new logic for phase 2 and for phase 3. And you probably would make each phase into its own separate subtree, instead of just having one subtree that gets reused with some slightly different parameters. But how do we decide when we go from phase 1 to 2 to 3? Well, we do that based on our octopus tentacle array, because this keeps track of just how many tentacles we have. Ideally, you would just do this on a transition normally and just check this with a normal condition. Unfortunately, the conditions don't allow us to check a array length, so we need to real quick make one. Super easy to do though, so let's just go up in here, make a new state tree condition, and we'll call that stc check array length. And here we can get a description. We don't really care about that. That's just for displaying, well, some explanation as to what it is in the actual interface. We care about receive test condition. This is going to tell us, hey, can we or can we not do whatever this condition is trying to check for. And in my case, I'm going to pretty much just hardcode this to work on the boss itself. So we'll make a BP octopus boss reference, and we're going to set that as category context so that the state tree is going to automatically fill it out for us. Very nice and simple. And then we'll just get the tentacles array, get the length of that array, and we'll just check if that is less than or equal to a certain amount. And that certain amount is going to be a variable. We'll let check against or something like that. And we'll set that to being exposed. And that's just going to be the return value for this test condition. Again, this is one of those things that you might want to set up a little bit more generically if you want to be able to use this condition for a bunch of different types of enemies in the future. We're just going to stick with it this way. So in the octopus boss now, we can set this up as a condition, state tree condition, check array length. And we can just check, okay, phase 1 to 2, if we have 6 or less. And then we enter phase 2 of the fight, because then we have proven to the fight, hey, we know how this works. We've taken out 2 of the tentacles. 1 can be an accident. Once you've taken out 2, you understand the fight. Then for the majority of the fight, we're going to be in phase 2. So we set up a transition, we make the condition, and we say, okay, once we have gone down to 3 tentacles, well, or less, but realistically, it's going to be 3, then we want to go down to the last phase where things get ramped up a lot and things are going to be a lot quicker and a bit more difficult. And that is how we decide to move from phase to phase. But these are just the condition checks. These aren't actually driving when these things get checked, because these are just on state completed. But these states never complete. This subtree that we're working with is a loop. It's never going to complete the tree as a whole. So these states are never going to get completed. These conditions, these triggers are never going to run. Instead, these are going to run on an event basis. We can send through events, and the required event can have a tag. And as long as we send in an event to these state trees with the same tag that we're looking at for here, that is going to be the thing that is going to trigger checking this condition. And if the condition is true, then we transition to, well, in this case, from phase 1 to 2, and then from phase 2 to 3. So both of these are going to be on event instead. I've already made a tag here, a gameplay tag in AI, combat damaged. So whenever we get an event with this specific tag, it's going to try to do this transition, and it only will be allowed to do it if the condition here is met. So we'll do that in phase 2 as well. The tag is going to be AI combat damaged. We already have something set up to respond to a tentacle getting damaged and getting killed. And that is simply in the octopus boss. On begin play, we're getting all of the tentacles, keeping track of them in this array. And then we're binding to every individual tentacle when they are destroyed to remove them from that array. That's already something that we're doing to make sure that we're never trying to access a tentacle that no longer exists. But at that point, whenever we remove a tentacle, that is a damage event. And in response to that, we want to get in our state tree, as I did just now, and we can just send an event to that state tree. If we right click on this pin, we can split it. You can see we can give it an event tag, and we just tell it, hey, we just had the AI in combat damaged. And our phases now just work. A very basic setup. Again, you probably want to build this out a little bit more with unique logic to phase 2, phase 3, maybe add in the possibility to do random new abilities that you can't do in phase 1 or phase 2 to really make it ramp up in difficulty and spectacle, beyond just having the same thing happen but faster. But then again, for a lot of very basic type of games, bosses become more difficult by just having them do the same stuff but faster. Important though is going into the octopus boss blueprint itself, and in the state tree making sure that we're using the octopus boss and no longer the octopus boss phase state tree. And once we have done that, we will see that we start off with a relatively slow setup here. As we can see there, started off a little slow. It does 1 attack, and then it takes a good little while before the next attack happens. And because I have these spaced out about 7 seconds, I'm essentially just getting attacked by 1 tentacle at a time. But when I've taken out a couple of tentacles, which we're going to see here in a moment, when the next one pops down, I've now taken out 2 tentacles. So it's going to start in with phase 2, and things are going to be a little faster. You can see it's now doing the next attack before the previous one has quite finished going away. And if we set these up to also have damage when we just run into them, we don't have that right now, this could become kind of tricky kind of quickly, right? Because now I can't just run away easily in any given direction. I need to take into account where these tentacles are blocking off my path and that kind of stuff. And if I just take a couple more tentacles here, just one more, it's going to become even faster. And the 2-second delay might even be a little too fast for only having 3 tentacles. But yeah, it's more or less constantly going to just say, hey, the moment I have an available tentacle, it's gonna be attacking, man. And that is going to be the, well, difficult part of the boss fights. Then all we need to do is have something in the boss fight here where if all the tentacles are gone, like this, the boss fight itself just plays an animation and it dies. And there's a bunch of errors that you might run into here because we're trying to set the actor location on an actor that might have in the meantime died. So we can convert this one to a validated get, where if this is valid, it will do that. And if it is not valid, what we'll do is we'll just delay for like 1/10 of a second so that we don't get into any infinite loops, and then just right back into there to try to just pick another one. Picking another one should generally just instantly work. This delay is just here, just in case we do this again and we get another actor that is not valid. If it happens a couple of times in a row, your game might freeze up for a bit. In realistic terms, that's never going to happen, but just adding in a little extra delay forces that to be spaced out and not all be done within 1 frame. And that should take care of pretty much all of these errors. And this boss fight is starting to be like a proper boss fight now. So let's just real double quick go back into the attack montage that we have made before, because I do want to, I think, it's actually in the animation itself, I just add in a second notify track and stack these two on top of each other so that the hurt box keeps existing for a good while longer. And that way, if we run into these, it also ends up hurting us. The only thing that we need to take into account is if we jump onto these, we don't want that to obviously end up hurting the player. So you do want to test this if the hurt box and the hitbox are separated enough so that you don't end up colliding with both of them within the same frame. Because this hurt box might be a little on the big side, to be honest with you. Hurt boxes oftentimes will be a lot smaller than the hitboxes. There still is a minute chance that if your frame rate is really low, you enter both of these inside of the same frame. But the chance is not that big of that happening. You might want to set up some code though that checks when you're entering the hurt box to see if you're also inside of the hitbox, and if the hitbox is currently available, and then checking your downward velocity, just like you do with the hitbox itself. As a whole, just making sure that your hitbox is bigger than the hurt box is probably as much as you need to do in order for this to work. Effectively, we now do have the boss fight. So next time, one more pass over the code to make it just improve the attacks a little bit, make it target toward the player a little bit more, and make sure that they don't overlap with tentacles that already are taking up a place. We technically have a functional-ish boss fight now, but there's still a couple of issues, and just generally a little bit of refactoring might be in order. First and foremost, it slams down these tentacles entirely randomly, which honestly not that big a deal, but it might be a good idea to make these guys try to target the player so that the player feels a little bit more in danger. And if I just make these go a little bit faster, we also have that issue of it being possible to damage myself while damaging it, so that needs to be fixed. But there is an issue where these can really clip through each other, which isn't happening right now, but it can. And as we start making these things target the player, there we go. There it will do it. Oh, no, it will not. But as we start making these things target the player, that's going to start happening more and more and more. So those are going to be the issues that we're going to be fixing and just generally improving the code for this thing as a whole. I also think that it probably isn't a bad idea to move all of these elements just back a little bit, because it's not super obvious when these things pop up that they aren't about to attack you. So just making these things go back a little more probably makes it a bit more clear what happens when. Again, there we got damaged while it shouldn't be damaging us. And that is something that has a bunch of different ways that we could fix it. The issue is the hurt box is turned on for the entire time that this thing is down, even while the hitbox also is available. And usually you will overlap with the hitbox, which is the outer one here, way before you interact with the hurt box, at which point you will be safe from being hurt at all. But it is possible, especially at somewhat lower frame rates, to enter both of these on the same frame. So the hurt box, before damaging the player, is just going to need to do a couple of extra checks. Number one, it needs to check if the hitbox is currently active or not. And we can do that with just get generate overlap events. Because if it is not currently active, no matter what, if we're hitting the hurt box, we need to just damage the player. No ifs, ands, or buts about it. That's just how that's going to work. But if the hitbox can currently generate overlap events, so this actually should be in the other pin of the branch, then we need to check, hey, is the player also eligible for hitting this tentacle, yes or no? And that we just do with this little bit of code here. So really, what we want to do is we want to collapse all of this down into a function. Selecting it all, right-clicking it, and collapse the function. It took me a while to find that button, and call that something like can player damage tentacle or something like that. I then also would very much like to convert this to a pure node and rename this like player character for the input, and is falling, which I realize now that we could just also use the is falling variable that exists on the character movement component. Might be a little bit easier. That's essentially what this does anyway. But now that we have this, we can just copy these two nodes over and make it do that exact same check if our hitbox is allowed to generate overlap events. Because what we're doing now is when we're entering the hurt box, checking the hitbox for if it is allowed to generate overlap events. If so, this is going to check if, exactly the same as down here, it should be prioritizing getting hurt instead of being hurtful, if that makes sense. Because if the player is hurting this thing, we don't want it to hurt the player. So we just connect this up. If the player can damage the tentacle, we don't apply damage to the player. But if it cannot apply damage to the tentacle, then we connect this up back to applying damage. And that should fix the first big issue that we had. So now we pretty much never should have that issue. We do have an issue, however, now created where it doesn't bounce us upward. And testing this out, it is a little inconsistent which one of these two colliders triggers first, and that is important for some reason here. Because the behavior, if this one triggers first, is a little different from if this one triggers first. And we can try to troubleshoot that and try to figure out why that is happening and how it is happening. We also very much can just make this hurt box, delay it always just by one tick. That way we are pretty much guaranteed that this is going to happen after this. Everything should still work pretty much the same, still should feel pretty responsive because one tick isn't that much in the grand scheme of things, but it does guarantee that we run one of those colliders before the other. The other way that we could do it, which is a little bit more robust, but might also have other issues with it, is instead of doing this, which is a bit hacky, we can set them to different ticking groups, which is somewhere in here. If we just scroll down, I might have scrolled past it. You can also just look for tick. And here we have the ticking group. Both of these are during physics at the moment. Since they don't really interact with anything at all, we could also just set one of these to being pre-physics or post-physics or post-update work. So if we set the hurt box to just run post-physics, it's going to be running in the same frame. Everything is going to pretty much just run the same way. But because this one is now set to running during physics, and this one is set to run immediately after physics, it's going to force the hurt box to always run after the hitbox. And that also should fix up all our issues that we had. If you have colliders that need to specifically always run during physics and they can't be in different tick groups because of that, there's very specific use cases for that being the case maybe. You can still kind of just cheat it with delaying it one tick. Either way works. This is technically a better way of doing it if you don't have a specific reason that you can't do it this way. Which brings us into improving the AI of this guy, because right now he is just randomly slamming down those tentacles in, well, random places. And we want that to be in a place near the player, and ideally in the direction that the player is currently going. And if we parameterize that, that's going to be another thing that we can ramp up in difficulty. It can be a bit better about predicting where the player is going to be, so that the player needs to more constantly keep going back and forth and changing directions, changing speeds to prevent being hit. So let's open up the state tree task for the octopus attack, because right now what we're doing is we're just getting a random float in the range between the starting position and the ending position of where we're allowed to make these things go. And because we need to find out where the player is on this left to right spectrum, and the distance is kind of irrespective of its depth. Whether the player is here or here, that doesn't really matter. We just need to know how far along, left to right, it is on this platform. Because that is going to allow us to get a random value closer to where the player is. And also, we want to go ahead and store that value for future use so that we don't set any other tentacles super close to that value while it is being occupied. So, how do we calculate that? Well, that is the big question, isn't it? Well, before anything else, to make this just easy to work with, what we're going to do is we're going to, well, get the player pawn as well. So get player pawn. And we're going to get the actor location from that too. We're going to be working with a bunch of values here. And I think it is easier to understand if we just kind of normalize these. So we're going to say the starting point is going to be equivalent to just 0. The ending point is going to be equivalent to, well, whatever the ending point is. And then we just need to figure out where that actor exists between those 2 points. Make sure that these aren't in any weird way rotated. That makes this so much easier to deal with, because they are both just on the X of 700, the Z of 100, and the only thing that really differentiates them is the amount that they are in the Y position. So minus 800 and plus 800. If we can count on that being a fact and not these being offset diagonally in some weird way, that makes this math a whole bunch easier. Because then what we can do is we can just figure out where just the Y location of our player is between these 2 points. If we need to figure out any type of diagonal line here, it's going to be exponentially more difficult to deal with. Since this is a beginner's making your first game course, it's going to be easier for you, believe me, if you just set up this level or whatever level you're making in such a way that you can have these 2 points just on the same straight line instead. Keeping that in mind, that's the way that we're going to do it. And we need to figure out, okay, so just the Y position of all these 3 nodes is what we care about. So we'll just break vector for all 3 of these so that we can work entirely off of the Y position. I'll remove this lerp vector. We'll re-add that in a moment, but for now, that might just otherwise cause confusion. We need to do an inverse lerp. So instead of giving in 2 locations and giving in a percentage of where we want to be between those 2 locations, what we're going to do is we're going to give in our Y position alongside with the starting and the ending points, and it's going to give us back what percentage between the start and the end our Y position exists in. So we start off with our player pawn's Y position, and we subtract from that the starting position. So that's going to be our starting point, Y. We subtract from that. And that we divide by our B position, our ending position, subtracted with the starting position as well. For anybody who cares about the math, what it actually looks like would be value minus A over B minus A. And that will be our, usually we call that T, that's going to be our time, our alpha, our value that we care about. Now that we have that, we very easily can just re-add that lerp that we just removed. Again, I just removed that mostly to clean up clutter a little bit. Going from our A to our B, and we're going to be using this alpha for that, and that is going to go in there. Now it's going to always exactly spawn these things on top of where the player is. And before we move on, it is good to test if it actually does do that. So let's test it out. And yes, in fact, it very much does do that. Now you will see The new one is going to spawn in and exactly at where the player is. No difficult trigonometry needed. We just took care of this with clever level design to prevent having to do a lot of extra math to make up for the fact that these are weirdly rotated or offset. But now they're always just spawning on top of the player, which is not what we want, right? We want this to spawn a little bit around the player and ideally in the direction that the player is looking. So first and foremost, let's make it spawn in the direction that the player is currently moving in. And for that, we can very easily just get the velocity of our player pawn. If we multiply that by just some number, so let's right click on this and turn this into a float, and let's say we multiply this by 3. If we get our actor's location and add to that our current velocity multiplied by 3, we're going to get where our actor will be in about 3 seconds. This is not exactly seconds, but it's close enough. And that is what is going to go into here instead. For now, let's keep this at a value of 1, because multiplying this does kind of make it go bananas very, very quickly, because 3 seconds walking in a certain direction is further than you would probably imagine it to be for the most part. So yeah, it still just spawns in when I'm standing still, but if I'm walking around, you will see that it will spawn it in a little bit ahead of where I am going. But it also spawns it outside of what should be the bounds of our boss arena. And that is because it is now putting in this value, adjusted for my velocity, into this inverse loop. And that inverse loop can very much give values below 0 or over 1. And this loop can take in values below 0 or over 1. And it will just extrapolate on, well, these positions. It knows what a certain percentage difference between these is. So it can just extrapolate either outside of A or outside of B. So what we want to do is we want to clamp that float between 0 and 1, so that it never goes outside of the allowed bounds. With that, we can just kill this one tentacle, and then the next one will spawn in a moment. It's already starting to feel a lot more dangerous. It's actually targeting me right now. It's not just randomly doing stuff, and there you see, it is clamped to the outside of the platform's edges. But as a boss fight, just makes it a little bit more difficult, a little bit more dangerous. Maybe 1.25 is more what we should be predicting for, and that is mostly up to you to see, hey, how much randomness or how much prediction should be taken into account when I'm doing this. And 1.25 seems pretty good, maybe even a little bit more. This might be a little too exact. So what we can do is we just do this, where we do, hey, 1 plus 0.3, and this is the 1.3 that we just had before. Splitting this out just makes it a little easier and more obvious to see what these numbers mean. Now, all that we do is we just add a random float in a range, and this range is going to just be some number, and this number we will promote to a variable. So we'll call this random, expose that so that we can use this on a per instance basis. The random is going to go into the max, and then we just do random in a subtraction node or a multiplication node with -1. 0 minus random is going to be the minimum, and just random is going to be the maximum. Let's set the default value for this to something like 0.2, and that's going to make it be pretty random as to how accurate the prediction for this thing is going to be. It was very, very far away there, but now if I just keep running, it can just get clamped to this side, which is a little abusable, I guess. But this one was a lot closer. So as the boss fight itself starts speeding up a little bit, this can start being pretty chaotic. And with a little bit of randomness thrown in, it's going to be a bit more reactive than just being able to exactly predict where these things are going to be spawning in. We now just need to parameterize that. So in our boss phase tree, our attack has this randomness to it. Just promote that to a parameter. And in the octopus boss itself, now every single one of our phases also has a randomness value to it. Now it is up to you to test whether or not higher randomness or lower randomness makes it more difficult. I would actually hazard a guess that more randomness makes it more difficult. So we're going to set this to 0.05 randomness for phase 1. Then we're going to set this to 0.15 randomness for phase 2. And then like up to 0.3 randomness maybe for phase 3. especially if there's a lot of things happening at the same time and there's that amount of randomness that gets added into it as well. I think that's going to prove more difficult than it becoming more and more predictable because it becomes more precise. So as I kill these tentacles off one by one, the first couple of ones are going to be relatively slow here, but then we're going to have these pop up really quickly after each other. And phase 2 also is going to be a little bit more random than phase 1 was. And then once I kill this one, phase 3 is going to start. These tentacles are going to start popping up all over the place, and they end up just kind of stacking up on the sides. So maybe my platform just in general is a little too small anyway. And there's definitely something to the idea of maybe making the animations for the attacks a little faster as well. I think I'm just going to increase the size of the platform a little bit here, and then obviously move both of these targets. And because this is all done proportionally, as I move both of these targets, all of the code otherwise is just going to maintain all of its functions, and everything is going to just work the way that it is supposed to work. There probably should be a little bit of a waiting period in between going through phases, because going into a new phase immediately triggers a new attack now. So that's not ideal. I think having a just like herd animation in between, well, this is very abusable, isn't it? Now we're adding the randomness at the start here, which honestly can be fine because it's entirely based on velocity. What we also can do is, instead of the randomness being added here, we can add it just before the clamp, and that way it is not based on our velocity multiplied by some random value. It's our velocity multiplied by a static value plus some amount of randomness, and that's going to prevent things from just entirely stacking up on whatever direction we're looking. And matter of fact, it might even make things attack us just behind us, and it's going to make things even a little bit more random. So I do think that taking this and before going into the clamp node, adding in the randomness there might make the boss fight feel a little bit more fun as well. Personally, I actually think it becomes a little too predictable and a little too cheesy if we do use the velocity here. So I'm going to just take out the velocity as an element altogether, and we're just going to rely on that randomness. And if that is what we do, I do want the randomness to be bigger at the start and then smaller toward the end here. We're going to turn that around. And I'm figuring this out live as we go, right? I didn't try this out before. I didn't set this all up in advance. I want you to see my process here as I just kind of figure things out and try to, well, test the ideas for this boss fight. And I think that works pretty well. So the last thing that we want to do is we want to implement some code that prevents two tentacles to spawning too close to each other. Because right now they can overlap, and especially since they're trying to target the player now, they will be overlapping a little. So the boss fight itself is going to be keeping track of every single one of its tentacles and what position it exists in right now between these 2 points. So let's open up our boss fight. And the way that we're going to keep track of that is with a map variable. A map variable is like an array, but instead of it just being a list that linearly keeps track of a handful of tentacles here, it is a correspondence between two pieces of data. So it is, in this case, going to be keeping track of the tentacles, so tentacle positions, and we make that of type BP tentacle. And if we change it into a map, we can give in a second piece of data, and that's going to say, okay, we can now look up reference to a tentacle and get back at what float position that thing exists. So we have these tentacle positions, and there we can see this would be a reference to that actor, and this would be the value of where it exists. So whenever we make a tentacle attack, it's going to need to give us back where it got placed so that it can place itself in this map. And then when it is done attacking, it should take itself back out of the map. So in the octopus attack state that we have here, which is starting to be a little bit messy, when we play the attack, what we want to do first is we want to get the reference to the boss that we have, and then we get the tentacle positions, and we just add to that. And what we're going to be adding, we need to give in the key, which is the object that we're referencing. In this case, that is just going to be our picked tentacle. And we need to give in what position we placed it in. And once again, since we're doing some stuff here based on randomness, we don't want to just pull this in and put it in there because it's going to have a different random value. we want to just set this to be a variable, and this will be the tentacle location. And don't worry, I will clean this up in a moment, but we just set that tentacle location float first, and then we use that to go into this alpha instead. So that way we know that we're working over the same value. And then that tentacle location can also go into this map. We can set that before or after we start playing the attack. That doesn't matter that much. But now we're at least keeping track of this. However, we need the tentacles to also get removed from this map again once the attack is done. And that is a little bit more tricky. So let's go into our tentacle blueprint to handle that, because we have this entire play attack thing where we play a montage, we set the actor's location, and we play another montage and all that kind of good stuff. But we want to start removing the reference to this tentacle from that map after this first montage, which is the attack itself, and then the retreating is done. All of this is just resetting it back to its original position. So in here, what we're going to do is we're going to make an event dispatcher, and that is tentacle attack finished. We can give that an input, a new parameter, and that's going to be a reference to the tentacle itself. We just call that tent for now. It's going to be of type BP tentacle, object reference. And then whenever we finish playing this animation, what we do is we call this event dispatcher. This is the exact same thing as what we already have in our octopus boss here, where we're binding to whenever this thing is destroyed. Event destroyed is just an event dispatcher that already exists that the engine gives you. Now that we've made this, we can also bind in the exact same way to this. And whenever we call out this event dispatcher through a node like this, it's going to allow us to run code on other actors to do stuff with, and also give through any of the information that the parameters take in. In this case, a reference to this tentacle itself is going to give through so that this octopus boss knows, hey, one of the tentacles just finished an attack, and it's also going to know which tentacle finished an attack. So on begin play, we're already doing a for each loop where we're binding to everything for every single tentacle. We can just also assign tentacle attack finished, and that's going to make a node here for us with an event attached to it, and whenever any of the tentacles finish an attack, this is going to be the code that runs in response to that. And all that that does is just get this map, and we remove the entry that surrounds that specific tentacle. We also, now that we have a system that signals when a tentacle is done attacking, can kind of improve the way that this entire thing works. Because right now what we're doing is we're looping over all of the tentacles, seeing which ones are attacking and which ones aren't attacking, and then if we accidentally pick something wrong, we're doing that again, and it's just not great. So the way that we can do this instead is just make the pickable tentacles array on the boss itself. So we only have to populate this once, and we don't need to recalculate it every single time. And we just set this to being the exact same thing as the normal tentacles array initially. And then whenever one of them is destroyed, it also gets removed from the pickable tentacles. Again, the exact same way that it would from the normal array. So we just hook that up, all the exact same method. The big difference here is that it's also going to remove and then re-add things to this array when the attacks start and finish. So when the attack finishes, it's going to remove the tentacle that just finished from the map that keeps track of all the positions. But it's also going to re-add it back to the pickable tentacle. So we just add this pickable tentacle. Then in the attack itself, we can get rid of all of this weird stuff. We don't need any of this happening anymore, like at all. We don't even need this pickable tentacle array anymore, because we now have that on the boss itself. So we just get pickable tentacles from the boss, get something random from there. And we still probably do want to just make a delay, but we can make a delay by 1 tick, in case we do pick something that is somehow invalid. At this point, with this setup, we shouldn't. It's important to note, but just in case, this is kind of neat. And then as we start saying, hey, play the attack, we just get our boss's reference with the pickable tentacles that belong to the boss. And we also remove the item for our picked tentacle from this array. Now, the boss itself is keeping track of which things it can pick and which things it cannot pick, and adding them back in once it gets told, hey, this tentacle is now finished doing its attack. So we don't need to constantly rerun that code on the actual state tree itself, which is just a little bit more neat, a little bit more organized. Speaking of organization, this blueprint is starting to be a mess. But we've just refactored and changed a lot of things very quickly. Let's step through this one step at a time, just so that we're all caught up with what we're doing here. In the boss phase, we enter the attack state. The attack state is going to run the attack task, which starts with try enter state. It's going to pick a random entry from this array that exists on the boss as an array variable. It's going to set that to a variable to keep track of. It's going to check if that is valid or not. If it is not valid, it's going to wait a frame and try to pick another random one. But it should always be valid, essentially. At which point, it tries to pick a location for that tentacle based on, well, everything that we did before. Sets that to a variable as well, so that we know that we're keeping the same float throughout the rest of our code. It uses that as a lerp alpha to pick a location between these two inputs. Then it sets the tentacle that we chose to that location. It adds to a map on the octopus boss itself that specific tentacle along with the location that corresponds with it, and says, hey, now that this tentacle has been picked, we need to remove it from the pickable tentacles list. Then we play the attack, which we don't need the is attacking bool anymore because we're handling that differently now. And the attack will play the attacking montage. That's all good. When the attacking montage is finished, this thing will call out, hey, my attack is finished. And that is something that the octopus boss itself is looking out for. When the attack is finished, it's going to remove it from that map that keeps track of where it is positioned, and it's going to re-add it back to being pickable for future attacks. That means at this point, all we need to do is make sure that this tentacle location that we picked is not too close to any tentacle locations that exist in this map. And that can be a little bit tricky. Let's make that into a separate function, just so that it's a little bit less in this noodly mess of blueprint. We'll make that a function, and that is get location away from tentacles. It's going to use our boss and get our tentacle positions, and it's going to take in an input of desired location, which is going to be a float from, again, 0 to 1. First, we need to compare this to every single thing in this map. And maps also have a for each loop. We can just compare this and check every single one of these. If we just subtract this value from that value, and we take the absolute value from it, so it's whether it's positive or negative, this is going to give us a positive number. We can just check, hey, is this less than, let's say, 0.1? Because if it is less than 0.1, it's going to be within 10% distance of one of these already existing entries in this map. And that's maybe not ideal. If that is the case, we want to keep track of that in a local variable. This is a variable that's only going to exist for as long as this function runs. Then when this function is done, the variable is going to get discarded. Next time the function runs, it's going to start with a fresh new one. It's not going to keep this value around in memory unnecessarily after this is done running. Local variables, kind of great. And there's going to be an array of all of the positions that are considered too close. So any position that is within that 10% range of our desired location, we're going to keep track of. Make that a float. We're going to make that, click on that and make that into an array. And this is the close locations. And we'll just add to that only if our absolute value here between these two is less than 0.1. You can, of course, tweak this to be whatever it needs to be. Then we're going to add whatever value was in the map into this temporary array. Now, at the end of this for each loop, we have an array that contains all of the too close locations to this thing. So once the for each loop is completed, we immediately just can check, hey, is there anything in this array at all? We can just check, hey, is this empty? Because if it is empty, there's nothing really we need to do. We just picked a location that is entirely fine and we're good to just place it at. So if it is empty, we add in a return node, and the return node is going to just have our desired location be given back as the actual location right away. But if this array is not empty, then we're going to need to do a little bit of work, because at that point, we're going to need to compare the desired location against every location that is already occupied and try to figure out a place that it can fit. And that gets a little complicated maybe. So let's go through this one step at a time. First and foremost, we get a reference to our boss from the context variable that we already have. And there we get the tentacle positions. Because at this point, if we have even one thing that is too close, we need to update our entire locations array to have every location that is occupied in it, because just offsetting it a little bit based on that one location might then move it too close to another location. So we need to compare against every possible location. Luckily, we can very easily just get the values by just typing values while pulling off of a map, and that gets you an array of all of the values with just the keys stripped out. And we're going to set our location array just to having all of those in it. We could make a separate other array for it, but we're not going to be using this for anything else anymore, so we might as well repurpose it. And we hook that up like this. But this is not an ordered list. This is a list of when they were added and then removed and then re-added, but it isn't in any way ordered from 0 to 1 or from 1 to 0. We need to sort this array so that we can easily loop over it and find an appropriate spot. I'm going to duplicate this here in a moment, such that we can both order it from small to large or from large to small. So it's going to have the same bit of code that we're going to be building here twice, with a couple of minor differences that we'll tweak at the end. All that to say, we're going to put in a branch here. For now, that's just going to have the condition always be true. We'll add in a random bool here in a moment once we've actually built out the entire thing. We'll take our locations array and we can very easily just say sort. We have a sort float array built-in function, and there we can say, okay, we want this to sort ascending from 0 to 1 or descending from 1 to 0. We're going to stick with ascending for now. And here we're going to go through all of the logic of finding a location to exist at. What we're going to do is, now that we have this locations array sorted, we can for each loop over it. And this is going to start at the leftmost tentacle that is currently positioned there and work its way up through to the rightmost one. And for each one of these entries, what we're going to do is we're going to check, hey, between this entry and the one over next to it, is there enough room between these two tentacles to place a new tentacle? And the way we do that is we get this value and we subtract from that the value of whatever is next in the array. So we get the array, we get a copy from the array of whatever is next. And the way we do that is the current array index element, just add to that 1. And that's going to get us whatever is next in our list. However, when we get to the end of the array, it's going to try to get something that doesn't exist. So we also need to build in a protection against that. And arrays have a built-in function for that. We can just check if something is a valid index or not. Because if it is not a valid index, we know, okay, this is going to be the last element of the array that we're working with. That is going to be the first and most important check. Hey, is the next thing in the array valid? Because if it isn't, we need to do some different logic. But if it is, we can check against the two elements that we're working with here. So let's add in a branch, and that is going to go in the first thing of our loop body. For now, we're going to just assume that whatever we're doing is going to return true here. And false here is kind of only a last resort. Only if it hasn't found any available spots for us to occupy, it's going to go through and reach the very last element of this array, at which point this will be false, and we'll program some other logic in there in a moment. If this is true, however, then what we do is we check, hey, this subtraction minus whatever this getting node gets from the next array element. If we do an absolute node in between there, we do the same thing that we've done before, trying to get the distance between two things. This is now just an absolute distance in percentage. So this could be 0.1, or this could be 0.5, or 0.9. What we want to do is we want to check, hey, is this distance greater than or equal to a certain amount? And this is the amount of percentage distance that needs to exist between two tentacles for this to say, okay, yes, there is room between two tentacles to spawn in a new one. And I'm going to say that it needs to be about 15% of the entire length of our arena. If there is at least 15% distance between these two, that means that there's going to be room to spawn in the new one. And if there is room to spawn in the new one, at that point, we come out of a branch node here for true, and we add a return node. And we're going to be returning a value for the actual location. That actual location will be whatever element we're working with in the for each loop here. And we're going to add to that the absolute distance between the two elements that we're working with divided by 2. And that's just going to get us the exact position between these two tentacles. So the exact center. If we divide the distance by 2 and we add to that the original's position, which is what this array element represents, we now have a workable actual location. More often than not, this is going to be the way that we get a value. But if it didn't succeed in finding anything and it got to the end of the array, that is where this branching node comes in, where I said, okay, we're going to come off this full spin a little later, and later is now. So let's come off this and add in one more branch, because what we need to do now is there's no position between any of the existing tentacles that we can occupy. So we need to check, hey, anything to the left of the first tentacle and anything to the right of the last tentacle, is there any place in either of those positions? And that's quite easy. We just get the locations array here, and we get a copy of just index 0. It's going to be the leftmost thing, the very first thing that we checked. And instead of checking it against the next thing in the array, what we're just going to do is check, hey, is this thing itself actually greater than our margin, which is going to be 0.15 here before. I want this to be a little bit more generous, so I'm going to set this to 0.1. Because if this is greater than 0.1 and there's nothing else to the left of it, that means that there's 10% of the arena distance that I can work with here to just spawn this thing to the left of. And if that is the case, we can add in a return node, get the value at index 0, and just subtract from that 0.1. And we have found a location to the left where we can just kind of panic escape to say, okay, at least we've got some place to put that. And then we do the same thing to the right. If this also isn't available, we just do one more branch here, and we just get the last index. And then we get a copy of that, use that last index in this getting node. And instead of checking, hey, is this greater than 0.1? We're going to check, hey, is this value less than 0.9? Because if it is less than 0.9, that means that the rightmost tentacle isn't quite at the edge. There's a little bit of room to the right of it still. And if that is the case, what we do is we just simply return, very similarly to what we did before, this gotten value plus 0.1, and that's going to go into the return node here. At this point, you are all but guaranteed to find some place that your tentacle is going to be able to spawn in at. If you still haven't found a place after all of these different logic checks, the issue might come down more to the fact that your arena just isn't wide enough, that you're trying to attack with too many tentacles at once, and you might need to reconsider some level design before trying to fix the code aspect of this. But still, there's one very last option where all of these checks, trying to find a suitable location, they all failed. And if they all failed, what we're going to do is we're just going to say, okay, in that case, just pull through our original desired location. It's probably going to clip through something, but at least it's going to spawn in and do its attack at the very, very worst case scenario. But this essentially should never run. But this is a little bit too predictable at this point, because it's always going to check from left to right, and that means that it's always going to prioritize spawning in tentacles to the left side of the player. So what we can do here is we can just copy over this entire bit of code, just Ctrl-C and Ctrl-V it down here, and change a couple of things around, just very, very minorly. We're going to change the sorting order to descending instead. So we're going to check from 1 to 0 instead of 0 to 1. And the only thing that we're going to change here is this first for each loop, everything is going to remain the same. The logic here is purely based on an absolute distance. The direction doesn't really matter here. The only thing to change, instead of checking our first entry here being greater than 1 and our last entry being less than 9, those two things need to be turned around. So we just copy over this less than 0.9, and that's going to be what we check up here. And this one is also, instead of subtracting, we're going to change this to adding 0.1, because we're essentially just inverting what we're checking, right? We're checking the right first now instead of the left first. So we just need to take these two nodes and put them here, and then take these two nodes and put them in here. So we can just take these two out, replace these like that, and we just get this, check if it is greater than 0.1, and if so, we return that minus 0.1. And then the actual location for the very last node here, again, this is just a worst case scenario, fallback on a fallback on a fallback on a fallback, should never happen, but that is just going to pull through the original desired location, so that we at least have something happen there. And now we have that variant that goes the other direction. Now, in this branch here, which we've just set to condition true always, the full spin is going to go into this bottom one. And if we pull off of this and we just say, hey, I want to have a random bool, is going to, whenever it gets to this, randomly do the ascending sorting or the descending sorting. And now it can either 50% of the time favor going to the left of the player, or the other 50% of the time going to the right of the player, while still doing all the checks to make sure that it puts it in a position where it is valid and it's not going to overlap with any other tentacle, except if every possible check that it can do fails. And doing that, we will see if I just take out a few of these tentacles for the first phase here, and let's see, do any of the tentacles overlap here? No, and that one favored it to the right there. And now we're going to, at some point, have one that just managed to sneak in just between the two existing ones. That one favored a little bit to the left, and that one favored to the right again. So we now have a boss fight that takes into consideration where the existing tentacles exist. There might be one last issue, though, and that is if you kill a tentacle, it doesn't get removed from the map. So the map is still going to take the consideration of where it was when you killed the tentacle, and that might make it avoid certain positions while there aren't any tentacles in that position at the moment, because it thinks that the dead tentacle, it still sees that float location as being occupied. But that's not that hard to fix, because in the octopus boss itself, we already have on begin play a loop that binds on every one of these things being destroyed, and then we already remove it from the array of tentacles. We remove it from the array of pickable tentacles. All we need to do is when it gets destroyed, we also just remove it from that map. As easily as that. We already removed it from this map whenever an attack is finished, because when the attack is finished, it is no longer occupying that spot. But if this never runs because it got destroyed, we also need to remove it from the map when it gets destroyed. And once we have accounted for that, the boss fight as a whole pretty much works. But we really are starting to get into some very noodly messes. We're expanding the amount of code that we're making in Blueprint, and this is just kind of hard to read, right? So next time, before we move on to really polishing up how this boss fight looks and how it feels, it's a good moment to just take a step back and clean up some of our Blueprint so that it is better organized, easier to read, and better to work with in the future. Now that we've done a lot of work on setting up code for a boss fight that we're going to be working on here, before we move on to the art, animation, and juice department, I think it's good to take a moment and go back over the majority of the code that we've made in this entire series so far, and make sure that it's not a total mess, because we have a lot of stuff that is just kind of hanging around at this point. Like this. Is it very badly organized? Not necessarily, but it could be better. So let's go through and make sure that everything is properly organized here. First and foremost, the begin play of our player character. We have a lot of stuff just hanging off of this, and it's kind of weird, and it's just, I don't know, don't love it. Most important thing to get started with is just making sure that we select some nodes, press the C key to add a comment, and we'll give that a name, and we'll call that begin play. Everything that runs in begin play is going to be contained within this section, within this comment of code, so that we can easily at a glance see, oh, this is begin play. I want to see something in begin play. We can go right over here. But then within that, we're still going to add in more comments. This is set up initial bars, like the gravity scale and the initial transform. And if we want to have anything else in the future, this is where we add it into. We can give these comments different colors as well. So the begin play itself, we can maybe make like a yellow color, and then within that we can make these like green colors so that they are a little easier to differentiate from each other as well. Then we've got a bunch of things that set up bindings. So we also organize these, and instead of making this one very long string of just nodes after nodes after nodes, I'm going to add in a sequence node. And this is just purely for visual purposes, so that we can put them a little bit more clearly under each other. So we're going to set up this binding here, and then we add one more thing into the sequence, and that's going to set up a binding as well. And now these can very easily just be moved in such a way that they exist vertically under each other, exactly like this. And now that they're all under each other, it's first and foremost good to encapsulate these individual sections in comments as well, so we know which nodes belong to which section of binding setup. So just comment all those. We'll give them names in a moment, and then we can line these up as well, like this. And then everything is encapsulated in the larger begin play comments. This is bind on HP update, bind on player destroyed, and this is bind on movement mode change. So bind movement mode changed. Then we have all of the jumping code for the player. So we can just encapsulate that in a comment, call it jump, move it over here. It's fine. This stuff is the jump dash, which also is a little messy, visually speaking. But this is part of platforming too. So let's call this air dash. And then this is on event landed, comments, landed. And even if we don't do anything about making these a little bit less noodly, making these a little less all over the place, the fact that they're just encapsulated in some comments now makes it immediately more obvious that, okay, I'm looking for a specific thing, it's right around there, and this is everything to do with it. There's no question that any nodes that exist here are related to anything that is happening here, just because we've got literally a couple of rectangles around it. But these things are both related to player death, so we'll make here kill player, and this will be reset player, and then both of these comments together I can comment around again, selecting them both, make a comment, and we'll call this player death. Then we have a bunch of input stuff here, which once again we're going to per event just put a comment around. So comments, this is jump, and that's going to probably be good to have the air dash, which also is input related actually, and our jump event itself be close to. So let's move these two both over into a position where that makes sense. Then event landed can move back up here, and we're going to lay this out in a way that makes some amount of sense. So this is the jump event. I think what I'm going to do is I'm going to put all the inputs on top of each other, and then anything that responds to those inputs is just going to go to the right of that set input event. So in this case, we have the jump player, which does a couple of basic things, among which is call player jump, which then exists directly next to it. This is damage, so this probably goes close to where our player death is, because those are closely related, obviously. And this is input move, so we select all that, point it as move, just move it aside from now. And this, I think, is camera inputs. So camera inputs, and we can move both of those into our stack of input events. And we only have this one left, which is the bounce attack, which is part of jumping as well. So let's call this bounce attack, and we just put that in our row here that has to do with jumping, and suddenly we have a much more organized blueprint without actually moving around and organizing any of the individual nodes. Simply through the sheer matter of putting some rectangles around it, things have instantly improved in readability. Make things a little bit better by removing all these like double noodles. I find them to be distracting and ugly, so it's generally just a little nicer to have two of the same node. This functionally doesn't do anything different than having two of those noodles. It just, as your blueprints grow, getting in the habit of doing this instead of having one reference to it that goes all over the place and creates a bunch of lines all over your screen is just a little bit easier to keep track of. And then things like this, like and dash, there's no reason that this line needs to cross these other lines and make this visually noisy. We can just put this one up here. This node doesn't even get used anymore. Don't know why it still exists. This can just be a straight line. No real need for that to like go up and down all over the place. And once we start implementing all that as well, things do very quickly start becoming a lot less chaotic and noisy. And just making sure that you generally don't have too many lines that intersect with each other. There's no good reason for this to exist here where these lines intersect, which on a large scale does make things harder to read and more difficult to follow along. Just move it down here. There's no intersecting lines, and it's going to be a lot clearer what everything is connected up to. Then, of course, we also have, instead of just events, a bunch of things that are simply just small functions. And there might be some things in these events that could definitely do with being functions. Some things can't exist in functions, like these latent nodes that start at one point and then end at some point in the future. Those need to exist in your event graph. Delays, same thing. Those need to exist in your event graph. Timelines, once again, can't be in a function. Needs to be in the actual event graph. This bounce attack, why even is this an event? There's a couple of very quick little nodes. No real reason for this to be an event. Nothing about this requires it being an event. So we can just convert to a function, which we can right-click on the event, convert event to function. Now it doesn't clog up our event graph anymore, and it just gets added to our function list over here. Functions can be given categories as well, which is really quite nice. So these functions over here are all to do with HP. So we can give this category stats, and then one of these vertical little lines to make a subcategory HP. And now we can see I have a category for stats and a subcategory for HP. I can now just add other things to that. So subtract HP, get HP, and same thing here. Set respawn transform. No reason for that to exist here in my event graph. It's just a little like over the top. It's just taking up space, right? So let's just convert that to a function. Player death. Again, nothing about this necessarily is benefiting from being an event. So we convert it to a function. And that way we can easily organize them with those categories. And we don't even need a lot of this. This event damage is actually an event. We can't make this into a function. A couple of nodes given after it, that's fine. Don't need to specifically make a function for this. And here, some of the stuff that we're doing, we rely on these delay nodes, so probably fine to have this all be in the event graph. Player destroyed. Why is this an event? We can just call this on player destroyed and turn this into a function. And if it starts screaming at you because it apparently is connected to some other nodes here that aren't able to go into functions, sometimes it does that, you can just disconnect this, select all of these, and collapse them to a function instead. And we can call this player death. And then instead of directly binding this event, because now we're trying to bind something that we've turned into a function, and we've been just creating events and hooking them up into these binding nodes, but we can just create an event, and we can take any function that matches the parameters that we're looking for and say, hey, bind this function instead of it needing to always be an event. So in this case, that would be player death response. Just do need to give it an input here, even if we're not using it. Otherwise, we're not going to be able to use the create event node for it. So create event. Now that we have done that, we can see we have player death response. And that significantly shrinks down our blueprint, footprint for this. And at this point, we don't even necessarily need to make this into like this sequence, because now it's a lot more compact. We just have a couple of binding nodes that bind to functions that exist in here. And only the things that really need to exist in the event graph now are remaining here in the event graph. Everything else we stuff into functions. And that's just the player. If we want to do this, we also probably should go into, for instance, this octopus boss, which has a fair bit going for it. For instance, this event tick, which we don't need anymore. There's not that much happening here, so it's not that big of a deal to just have this kind of hanging out. But if we go back into its attack that we made here, it's a bit messy, isn't it? There's a lot of stuff just going all over the place, and just, it's not really a good time. Let's just section this out a little bit. This is just pick random tentacle. We're not using these nodes down here anymore, so let's delete those. And then everything pretty much up to here, I would say up to get location away from tentacle. All of this probably can be one function, because all that then does is get us the tentacle location, maybe even include this all the way up to here. We can right click on that and collapse to function, and that is get tentacle attack location, and then we set it to that tentacle attack location, and then we add it to our array, or our map rather. And this entire thing has just visually been simplified so much. Of course, this is still a little bit of a mess, so we want to organize this a little bit more, because there's a lot of wires going all over the place. And that's the next thing that I want to take a look at, is when you do have a lot more math going on and just things connected up to each other and these things going all over the place, it starts just to look messy, and that's not great. Especially, again, if you look at this here, not a good time. Let's clean up both of these functions as well. Number one is just spacing things out more, man. Just making things a little bit more spaced out really, really does help. Putting things in logical locations also does help. This is going up here, and this is going down there. it makes a lot more sense from a readability perspective. These are just laid out in the opposite way. Then these get echolocations. It's kind of just annoying to have these two little yellow wires that then also have to cross around. So here we have them the other way around, where you just put this into B, this into the A. And that makes this just a whole lot less messy to look at. Compact all that together, put that toward the end here. There we go. Just a couple of nodes moved around. Look at how much more readable everything going on here is. You're going to have some wires crossing, that's just going to happen. I suppose it is doable to mix this up in such a way that we have less wires crossing than we did before. But there's going to be some of it happening. Not much you can do about that. But spacing things out in a way that they at least are clear as to where which crossings are going. Now, get location away from whatever is a visual mess. And the most important part here is that the desired location is getting hooked up to like 4 different return nodes all over the place. Input parameters can just be called as if they are local variables. So if I just get the desired location, anything that is hooked up to this, I can just hook into this instead. So that's going to immediately take care of a bunch of these very ugly green lines that just go all over the place and make this thing look unnecessarily chaotic. There we go. Immediately, a lot of the lines are fixed. Again, here, even if it's just a short run, we can replace that with it being as a local variable. Here, we're going to add some redirect nodes so that we can have this line like nice and cleanly going under everything else that is going on with it. Because there is just a little bit happening here, and I would like these nodes to exist down here. Again, don't be afraid to just create a little bit of room so that your logic can fit within the area before the branching nodes. That way you can just very easily look from left to right. Okay, this is what it's checking for this branch and then doing this. Just lining things up so that they don't have like weird wiggly lines all over the place also massively helps. And then this, instead of this going down all the way there, it probably helps to have this kind of on level with the rest. And then here we do just have a bunch of noodles that go all over the place, which is not great. Since this is a local variable, I can also, instead of noodling it everywhere, just add in multiple nodes that represent that array. First and foremost, will already clean things up massively. And again, just creating a little bit more room around everything, it does wonders, man. I know that I'm saying it over and over and over again, but it really bears just repeating. And for any of these long lines, again, that you do need to be physically connected, it's good to make a redirect node and just make them go all the way over or all the way under all the rest of your logic. Because that way, even if you're not adding in comments to this, which you definitely still should do, they also kind of work as a dividing line of, okay, this is one section of code, and then this is the next section of code, which just separating them with some distance, once again, does wonders of making them more readable. Because the code that's happening here isn't that complex. There's not that much happening. It's just because it's all so stuffed together, it seems a lot more complicated and a lot more bothersome than it actually is. Especially if we just move these a little bit to the right, so it feels like we're actually stepping through, first checking this, then checking this, then checking this. Just look at the difference between the clarity of what you see up here, even without it being commented, and the mess that we have down here. This is, with a couple of nodes switched around, the same code. What would you prefer to look at? This top one or this nightmare? I think next time it is a good moment to dive back into Blender and take our boss fight that we have and make it a little less super ugly and just placeholdery.